So let's talk a little bit more now on what you might have heard a lot about these p-values. So I hope that some of you at least are confused about what they mean about these p-values. You might be hearing every time, what is p-value? So before we go on to p-value, let's talk about hypothesis testing. It's used when we just need a comparison between two or more groups. And the choice of the test that we use for testing a hypothesis depends upon the format of the data and the type of the study design. Now, if we have more time towards the end of this session, I will talk in one slide about the study designs. But if we are done, or if people don't want, we will not talk about study designs on this session because that was not the initial draft. But let's say there is a research question, and this research question reads like, is there a difference between, let's say, A and B in patients of carcinoma cervix in terms of death? So this A and B could be anything. It could be the parity. It could be the smoking status, smokers versus non-smokers. It could be a treatment. So just that, is there a difference between A and B in patients of carcinoma cervix in terms of death? Do A wale people die more or do B wale people die more in a standard population of carcinoma cervix? So you can think that even if A and B were exactly the same, there was no difference. Yet when you do this study, the deaths will not be the same. A might have more deaths or B might have more deaths. If you have a large sample, then they will be near about to each other, but they will never be same. The dilemma is that any difference, it can be due to a real difference or it can always be due to chance. And when we do a study, we don't know whether this difference is coming because of real difference or because of chance. And statistics cannot prove or disprove. It can only provide you some evidence and leave it to your judgment whether you want to accept it or whether you want to refute it. So to make a null hypothesis, so again, this null hypothesis is a term which statisticians will use to confuse you a little bit more. So if you already are aware, if you are still with me after the end of this slide, null hypothesis will become very clear to you in the next slide. So if you are clear that our research question was, is there a difference between A and B in patients of carcinoma cervix in terms of death? Let's convert this into a null hypothesis. Again, no rocket science, absolutely simple. The null hypothesis will state that there is no difference between A and B in patients of carcinoma cervix in terms of death. That's all. So when we are saying a null hypothesis, that means it will create and artificially state that there is no difference. And to test this, we do what is called hypothesis testing, and which will explore how likely it is that the observed difference, how likely means, likely ka matlab, so likely can be said in terms of probability. So I can't write very well with this cursor, but I will try and write some. So when we talk about likely wala word, statisticians will replace this with the term probability to confuse you. What is observed difference? Obviously, when we've done a study, there is some difference. So don't get confused and don't get frightened by these terms. We are trying to explore how likely it is that the observed difference, the difference that we have observed in our study, is due to chance alone, assuming that the null hypothesis is true. That means if the null hypothesis was true, that there was no difference, then we want to see that what difference we have observed when actually there was no difference. How likely is it possible that it is all because of chance. And this 4 points are translated into what we call p-values. So p is a probability. It can take values between 0 and 1 only. It measures how likely it is that any observed difference is due to chance. So when the value is close to 0, it is unlikely that it is by chance. And when it is close to 1, it is more likely that the difference between the groups is only by chance. And the aim of the entire hypothesis testing is to gauge how likely it is that the difference is genuine if the null hypothesis is true. So reading this statement alone will probably confuse you and will frighten you. But if you read it in the background of these 2 slides, then I'm sure that this concept of null hypothesis will not remain any more frightening to you after today. So this is just an example. We were talking about A and B. Let's say that there are 2 groups in this, A and B. These are the numbers of death, and these are the number of total denominator patients in this group. This is number 1 trial, and there are 6 different trials which are listed here. So these are the odds ratio that were found. These are the 95% confidence intervals, and these are the p-values. Now, immediately, if you see the p-values, obviously, there is, this is when we talk about significant or not significant, I'm going to use the colloquial terms, although in 2 slides later, I'm going to tell you that you should never use these terms significant and non-significant. But for the purpose of understanding this table, you see there are 2 p-values which are significant. So there were only 2 of these trials which found that there were significant p-value of treatment A over treatment B. That means treatment A had an odds ratio of 0.3. That means people in group A were 0.3 times as likely to die as in group B. That means people in A were protected. That means the treatment A was protective as compared to treatment B. Now let's analyze the 95% confidence intervals. So here the odds ratio for 95% confidence intervals are going from 0.09 and they're crossing 1. They're saying 1.13. That means people in A group could have been 1.13 times dying than B. So it really doesn't help us. It is either way, 1 ke niche bhi hai, 1 ke upar bhi hai. Whereas when you look at the second confidence interval here in this second trial, it is staying on one side of 1. It's all less than 1. So that means the range is between 0.08 to 0.74. So in worst case scenario also, the treatment A was protective in this particular trial. And this is parallel with the p-value, which was significant here. If you do these in all these groups, you will see that it's on either side of 1 and it doesn't work correctly. So this is wrong. This confidence interval is actually 10.0, 10.7. So again, we have a congruence between the p-value and the confidence interval. That's all I wanted to show you here. And this particular confidence interval was also important with a p-value of 0.007, which is significant. So if you are still with me, let's say, let's go here. And these were the only 2 confidence intervals which were found not crossing 1. And we had p-values which were significant in these areas also. 4 points I want you to remember about the p-values. So the p-value depends upon the number of patients in the trial. So you see here, the p-value was 0.007 because this trial was extremely big. It was the biggest trial of all these. So they had a lower p-value, no problem with that. And the size of the p-value also changes with the size of the observed effect. The size of the observed effect means the level of the odds ratio. Another thing, the classification of significant versus non-significant is now getting obsolete, and people don't like it calling it significant p-value or non-significant p-value. It's better to report the actual value and allow the readers to make their own judgment whether it is effective or not effective. And there is no relation to clinical importance. So in this trial, we might have found that the p-value is very significant. Or you might find that if you have a sufficiently large group, you might be able to prove that giving treatment X will reduce the length of time in labor by 1 minute. And it is statistically significant with a very high p-value. But really speaking, does it matter if you reduce the labor time by 1 minute? So we have to make a practical judgment to see whether it is clinically important or not, although the p-value itself may be important. The cutoff values of 0.05 that are often used are purely arbitrary, and they are often misleading conclusions. They give rise to misleading conclusions in whether accepting or rejecting the hypothesis. Because if you accept a significant result as real, there are still chances that you are 5% time you are wrong. And this is what is called type 1 error. Or you might realize that if you dismiss a finding just because it is not significant, then you may still be wrong. And this is called a type 2 error, and which is particularly true in small studies. Now, I'm sure that a lot of you will still be wondering what is a type 1 error and what is a type 2 error. So let's make it a little clearer here in this. So here the doctor is telling him that he's pregnant. Obviously, this is not true. So this is what we call a type 1 error, which is definitely a false positive. The test says that he's pregnant, but obviously he can't be pregnant. So that's a false positive, which is a type 1 error. And alpha is the probability that we will make a type 1 error. And we always ask for alpha and beta when they ask you to calculate sample size. So alpha is nothing else but the probability that we will be making a type 1 error. Now the next is the type 2 error. So what you see in this image, obviously the lady is pregnant, but the doctor tells her you're not pregnant. So this is what we call the type 2 error, or a false negative. The test says negative, but obviously the disease or the condition is positive. And this is beta, that is the probability that we will make a type 2 error. And what is power of a study? It's nothing but just 1 minus beta. So in your mind, if you remember this image that I have projected on screen now, and you see on the left side is the male patient who's being told that he's pregnant, that is the type 1 error. And on the right side, you have the type 2 error. I hope with this image in your mind, you will never make a mistake in what is type 1 error and what is type 2 error. So then p-values and confidence intervals, they're related to each other because they've been calculated using the same set of values. Both are closely related. And when you are making a presentation or when you are making a paper, it's always good to present them both on the paper. So again, with this, I stop